Welcome back to electronics. This is Dr. Robinson. In this lesson, we're going to look at voltage regulators. In our previous lesson, we introduced diode limiters and we examined circuits that could be used as limiters. Our objectives for today's lesson are to introduce voltage regulation and to examine diode regulator circuits. Here I have a definition of an ideal DC voltage regulator. It's a device that maintains a constant DC output voltage regardless of variations in the input voltage or the load. Let's examine the behavior of a regulator in block diagram form. Here I have the block representing the regulator. On the left side is the input voltage, a DC voltage applied to supply the power to the regulator. Now, if this were an ideal voltage regulator, this output voltage here would not vary with changes in the value of the input voltage. Now, typically, this input voltage is a voltage greater than the output voltage of the regulator. So say this were a 5-volt voltage regulator, then it would produce at its output 5 volts. A reasonable input voltage to that regulator would be, say, 15 volts. Now, if we have a circuit that uses in different parts different power supply voltages, we could use different regulators or multiple regulators to supply those voltages. So from this single input 15-volt supply, we could have one regulator that produces 5 volts for one portion of a circuit, and we could have another regulator that produces, say, an output voltage of 12 volts for different portions of the circuit. Now, let's add a load to our regulator. So here I'm drawing a resistor of value RL for load resistor. Now, this doesn't have to be an actual resistor. This resistance can represent the input to some circuit of interest to us, like, say, an amplifier, a cell phone, something that we need to power with a voltage supply. As this resistance value changes, for this output voltage to remain constant, we know that by Ohm's law, the current here must change. So if, say, I made this resistance smaller and smaller and smaller, for the output voltage across the regulator to be constant, this current must continue to increase to keep the equation V out equals IL, the load current, times RL, true. Now, in a practical regulator, there's some limit to the amount of current that can be put out of its output terminal. So that at some point, as this resistance becomes smaller and smaller, we will lose the regulation capability. Now, there are two figures of merit that are typically used to describe a regulator. These are the line regulation and the load regulation. The line regulation is the ratio of the change in output voltage to a change in input voltage. Now remember, an ideal regulator, if we change the input voltage, the output voltage would not change at all. So for an ideal regulator, the line regulation would be 0. Now for load regulation, that indicates how well the regulator can maintain the output voltages for changes in the value of this load resistance. So as I make this load resistance smaller, the current increases. If that current changes by some amount, ideally, for a perfect regulator, the output voltage would not change at all. So the load regulation for an ideal regulator would also be equal to 0. Let's examine the concept of loading by looking at ideal and real voltage sources. Here I have an ideal voltage source. If I put a load across this ideal source of value RL, we know that because of the properties of an ideal voltage source, no matter what the value of this resistance is, the voltage across this resistor will always be equal to Vn. However, a real voltage source, one that we can build in practice, has associated with it some sort of internal resistance, which I have modeled here as a resistor Rs. So this source, its output terminals are between here and here. Now, if we attach a load to this real voltage source, we can see that we have completed the loop around the circuit. Current can now flow, and the voltage here at the output of the source does not have to be equal to the input voltage because we can have a drop across this source resistor. If RL were an infinite resistance, such that no current could flow, or in other words, an open circuit, then the voltage we measure across the output terminals of the real voltage source would be equal to Vn, just as it would be for the ideal voltage source. We can write a relationship between the output voltage and the input voltage for this real voltage source using voltage division. The out is equal to, again, by voltage division, RL over RS plus RL times Vn. We can see that as the source resistance approaches 0, the output voltage approaches the input voltage, and the real voltage source becomes more ideal. Now, this concept of the output voltage changing with changes in load resistance is known as loading. We say that we have loaded the source because the output voltage is no longer equal to the open circuit output voltage. Let's look at how we can take advantage of the characteristics of a diode to implement a voltage regulator. Here I've drawn the characteristic IV curve for a diode, and you can see the expected exponential relationship between the current through the diode and the voltage across the diode. Now let's say this diode is introduced into a circuit and biased such that the current through it places it in this portion of the curve, this steep portion where for large changes in current, there are small changes in voltage. Now we can see that for this particular diode, I can vary the current through the diode from, say, 500 milliamps to 1 amp, and as that current is varied, the voltage across the diode changes only by approximately 50 millivolts. Now, as the current through the diode becomes less and less, we can see that, say, if we were operating in this region, then for the same amount of current change in the diode, we can get a much larger change in voltage across the diode. Now, it's the steepness of this curve that we can take advantage of to implement a voltage regulator. If, for example, this curve were a perfectly vertical line, then we can see that for any current through the diode, the voltage across the diode will not change. Here I've drawn a circuit that can be used to implement a diode regulator. This portion of the circuit is the regulator. This resistor RL is the load resistor attached to the output of the regulator. Now, say initially that there's no load resistance, or the load resistance is an infinite value. We can calculate the current that flows around this loop. We know that the forward voltage drop across a diode, when it's forward biased, is approximately 0.7 volts. So this current I can be written as I is equal to 12 volts minus 0.7 volts divided by R1, 100 ohms, is equal to 11.3 over 100 is equal to 113 milliamps. Now this current is chosen to bias the diode in the steep portion of its characteristic curve. Now let's say we add the load resistor to the regulator. When the resistor is present, some of that current, that 113 milliamps, can now flow through this branch. But because the diode is biased on the steep portion of its curve, even though the current through the diode has decreased, the voltage across the diode remains relatively constant. Now, as this resistor gets smaller and smaller and smaller, and we take more and more of the diode current away so that it can flow through this branch, we eventually reach a point where the steep part of the characteristic curve is left, and we lose the regulation. So this circuit can be thought of as approximately a 0.7 volt regulator, where that 0.7 volts is due to one forward voltage drop across this diode. Now let's look at how that circuit actually behaves in terms of its line regulation and its load regulation. On this graph, I have plotted the output voltage of the regulator versus the load resistance value. And you can see that for a load resistance value of 500 ohms, we have an output voltage of approximately 0.75 volts, one forward diode voltage drop. And you can see that the output voltage is maintained for values of 400, 300, 200, and 100 ohms of load resistance. Now, once we decrease below 100 ohms of load resistance, the current through the load resistor is such that we're pulling more current away from the diode, and it's leaving that steep portion of the characteristic curve. Now, for this particular curve, it turns out that a load resistance value of approximately 45 ohms results in a decrease in the output voltage by approximately 1%. So at this point here, the output voltage has decreased by 1% from the voltage it is in this region here. Let's look at how the output voltage varies with changes in input voltage. In other words, what is its line regulation? Now, nominally, that circuit we were looking at has an input voltage of 12 volts. This is a plot of output voltage of the regulator versus input voltage to the regulator. And this point here, the input voltage is 12 volts. We can see that the output voltage is 0.753 millivolts for that input voltage. Now, say for some reason the input voltage is changed to 15 volts. Well, if that's done, the output voltage is equal to 0.768 volts. So there's a very small change in output voltage for this relatively large change of 3 volts in the input voltage. And if we decrease the nominal value of 12 volts to 9 volts for some reason, we can see that the output voltage is still 0.735 volts, still a relatively small change in output voltage. So we can see that this circuit, for that 6-volt swing, the output voltage is relatively stable, around 0.753 volts. Now, the voltage regulator that we've been examining has a regulated output voltage of approximately 1 forward diode voltage drop of 0.7 volts. How can we build a diode regulator that has an output voltage greater than this voltage? Now, here, I don't mind at all if you want to pause the video and think about the answer to this question before I give it to you. The answer is, we add more diodes. You can see here that I've placed in series 3 diodes across the output of the regulator. Each one introduces a forward diode voltage drop of approximately 0.7 volts. So the total output voltage of this regulator would be 0.7 plus 0.7 plus 0.7, or approximately 2.1 volts regulated output voltage. Now let's look at how we can use a diode regulator circuit as a component of a DC power supply to improve its performance. You may remember from a previous lesson the process involved in converting an AC voltage to a DC voltage. Remember, we start with an AC input voltage, possibly from our wall outlet. We apply that to a rectifier, and let's assume the rectifier is a full wave rectifier. We then filter this combined AC and DC voltage to obtain an output voltage that is mostly a DC voltage, but still has an AC component. Now we can apply this voltage as the input voltage to a voltage regulator. And we know that a good regulator will produce a constant output voltage even when the input voltage has variations. So the effect of adding this regulator to our power supply is to smooth the output DC voltage of the regulator. So we can draw the output voltage of the regulator as, ideally, a straight line. The variations in the input voltage have been removed by the functionality of the regulator, its line regulation. So in summary, during this lesson, we introduced voltage regulation and we examined a diode regulator circuit. In the next lesson, we are going to look at the demodulation of AM signals, or in other words, you can think of this as a good start to building an AM radio. Thank you, and until next time.